Okay, and the final presentation of this session is throwing your weight around, fixing Tor's positional weighting.
Okay.
Thank you. Go ahead.
All right, this is work with my colleagues at the Naval Research Lab, Aaron Jager and Paul Syverson. Paul is here. This work started because I was always confused by the way that Tor did load balancing across positions. It's defined by a set of fairly gory equations. And we looked into it, we discovered some issues, and have some solutions that I'd like to tell you about. So in the Tor network, Tor clients create circuits to anonymize connections. They typically use 3 relays. The first relay is a guard, the next relay is a middle, and the third relay is an exit. Not all relays can serve as guards. Relays need high uptime and bandwidth to be guards. Not all relays can serve as exits. They need to allow connections to outside the Tor network to be exits. Relays in Tor have different bandwidths. So in order to balance their traffic across the relays, clients choose relays randomly proportional to the bandwidth of the relays. However, clients must also balance load across positions because not all relays can serve in all positions. For example, if there's relatively little exit bandwidth, clients should reserve relays that can serve as exits for the exit position. Like in this example, the clients are both using exits in non-exit positions, and they should probably not do that if exit bandwidth is scarce. In order to instruct clients on how to balance load across positions, Tor defines a set of weights. So to define those weights, let G be the set of relays that can be guards but not exits. Let M be relays that can't be guards or exits. E be relays that can be exits but not guards. And let D be the set of relays that can be guards and exits. All right. So then there's a set of positional weights W, X, Y, where X is the position to be selected for, guard, middle, or exit, and Y is the class of relays, G, M, E, or D. And you can see in this table that for the various classes, there are the different weights across the positions. For example, for the class G to be selected in the middle position, that's the WMG weight. And if there's a blank spot, that means that type of relay can't be selected for that position. So then in the end, clients actually select relays proportional to a product of the positional weight, WXY, and the bandwidth. So then to come up with these weights, there's a set of, like I said, equations, and those equations are defined across a set of cases that break down the possible network states. So to explain those various cases, another set of variables, G, M, E, and D will be the bandwidths of those classes, and then T will be the total bandwidth of the network, the sum of those bandwidths. And a key value here is T over 3, which is the maximum throughput of the network, because every circuit has 3 positions. So if you use a third of the bandwidth of the network in each position, then you'll maximize that's the maximum possible throughput of the network with T over 3. So then this list at the bottom of the slide is all of the cases that Tor defines in its spec and in the implementation for the network to instruct the clients on the weights. I won't go through all of these, but it's sort of a decision tree, depending on if there's a lot of exit bandwidth or a lot of guard bandwidth, or how they relate to each other. Just as an example, let's say case 2A1. The case 2, E and G are both less than T over 3, then goes to A. Also, the minimum of G and D, E plus D is less than the maximum of G and E, and then subcase 1 of that, G is greater than E, and so on. So there are 13 of these cases. Those are the ones I highlighted in bold. Those are the leaves of the decision tree for which there are actually a set of weights defined. So we looked back at the Tor network consensuses in the past to see what states the network has been. This is over the period 2009 and 2021. We'd also looked at 2022. It wasn't complete when we did it, which was similar to what had been in the previous years. You can see that since about 2014, there have only been 2 network states, case 3A2B and case 3B2. Although in the past the network was a little bit more diverse, in the past things are very different depending. Positional weights weren't even introduced, I think, until 2011. Okay, so just to give you an idea of what those cases that actually exist in today's Tor network are like, the top half of the slide shows case 3A, 2B, and there are the conditions around it and the actual weights. You can see some of those equations that define the weights. So as an example, I took an actual Tor consensus. That's the top left bar graph, and it shows how much bandwidth is available in each of the positions G, M, E, or D. There's a lot of G bandwidth. The next is D, and relatively little M and E. And this falls in this state because the relays available to serve in the exit position, the E and the D relays, even when you add them up, they're still less than T over 3, which you can see in the top right graph, which is how Tor actually allocates the bandwidth across positions. It tries to get as much exit bandwidth as possible. It still falls less than the T over 3 maximum theoretical throughput, but in this case, this is the actual maximum throughput. This is a load balanced set of weights. The bottom half of the slide shows an example of the other case that has appeared in Tor's past. This appeared in December 2021. The one difference here, it can actually balance, completely load balance, all 3 positions. In looking at these cases and their definitions, we identified 3 deficiencies in Tor's weights. So in the first deficiency, there's a case that doesn't maximize throughput. In the second deficiency, there's a case where it yields invalid weights entirely. And a third deficiency is that the weights are discontinuous, meaning there are network states that are very similar. You might add a single unit of bandwidth to a single relay, and it'll go to a different case. And then the way that the relays are used becomes very different. Maybe the D relays stop being used as guards and start being used in exits. I want to talk about the second problem, which is perhaps the most severe, which is that in this case 2B, 3B, the weights that are produced are invalid. So as an example, that bar graph shows an example of a network that would fit into this state. And the weights that result are not all between 0 and 1, which is what is required and what the Tor clients check for. They use a different normalizing constant than 1, but it's the same idea. So here the WGD value is negative, for example. So the Tor clients will check for that, and when that check fails, then they just set all the WXY weights to 1. And that results in a very unbalanced load, a very unbalanced network. For example, if you set the weights to maximize throughput, this network could have a throughput of 90. But because the weights fail to be valid and the clients all set the weights to 1, things aren't optimal. So the first thing that happens is the D class will run at a bandwidth, and that happens at 46.3, which is almost half of the actual maximum throughput. So first of all, I'll just say there's a simple fix for this. Take those 2 equations and replace it with the 2 equations on the right. That's a thing that the Tor could do at any time, and it would be very easy, and it would at least solve the first 2 deficiencies that I described. However, it doesn't solve the third deficiency, the continuity issue. Also, it's not as good as you could do in that you have some cases where you have multiple possible solutions. And you could take advantage of that. There are some weight assignments that might be better than others. And if you had secondary goals, secondary to the primary goal of maximizing throughput, you could start to achieve those secondary goals. And that's what we try to do. But first we looked at if an adversary could take advantage of these deficiencies to attack Tor. We looked at 3 attacks. If the adversary can add relays to cause it to go into the error state, if it can shift its existing relays by, let's say, removing the exit flag to cause it to go into the error state, or if it can exploit a discontinuity by adding relays to cause some class to stop being used as guard or start being used as guards. And there are reasons why an adversary might want to do that. But I'll just talk about the first attack, adding relays. As just an example of that, consider a network, this one following in case 2A1, that has a maximum throughput of 98.25. In this network, an adversary could add just 1 relay with bandwidth of 1, and that would cause it to change case to case 2B, 3B, which is the error case. And that causes the load balancing to get so much worse that client demand starts to not be met at almost half of what the optimal throughput is at 54.21. So a single relay being added with a single unit of bandwidth could reduce throughput by almost 45%. So we looked at if this is possible or how possible this would be in the past Tor consensuses. We looked at a period of 5 years and a period of 1 year. Overall, it would be a fairly expensive attack. You would have to add a lot of bandwidth, I mean, at least 25% onto the existing network in order to get it to causing the error state. So Tor's not really vulnerable to this kind of attack, I would say. Although you could get as much as a 24% reduction in bandwidth, even though you added at least 24%, kind of counterintuitively. Okay, so we propose a set of alternative weights that we believe Tor should adopt. We considered two possible sets of goals. When considering what one might do, there wasn't any clear best choice for us, so we came up with two, just to show that you could, I guess. I'll talk about the Alt1 goals in this talk. We introduced a new criterion, which is we look at the probability that if you add a new relay to a given class C, it's selected as a guard or exit, because that's very sensitive traffic. So we'd like to minimize that across all the classes as much as possible. So we define a set of goals, what we call Alt1. The top goal is the same as the existing one, maximize the smallest position bandwidth. But then we say, let's maximize the amount of D bandwidth put in the exit position. D relays have the guard flag, so they've been around for longer, so it's harder to get, and that's a very sensitive position. That's a thing you might want to do. Then we say minimize the maximum VC value, minimize the second largest VC value, and then maximize the second smallest position bandwidth. And the idea is to satisfy these goals in order. So satisfy the first goal as much as possible, then subject to that, satisfy the next goal, and so on. So we derived weights for both of these sets of goals. I'm going to talk about the Alt1 weights that we derived. They're also, by chance, given in 13 cases, not the same ones, though. We proved that our solution is the unique solution, which is also different. This set of goals is exhaustive. You can't add any more goals anymore. The weights are already defined. It is the case that the current weights are the same as what the Alt1 weights would be in the most common Tor case, case 3A2B. But the second most common existing case, case 3B2, is different. So for example, the network in the bottom left, the current Tor weights are in the middle, but the Alt1 weights would be on the right. And as you can see, it allocates more of the D bandwidth to the exit position. The D bandwidth is in the gray, and it tries to put as much as possible subject to bandwidth maximization to the exit position, and then it kind of allocates everything else to maximize bandwidth after that. Okay, so some discussion points. We disclosed these deficiencies to Tor last year. They had already observed that the invalid weights were sometimes produced because they had a test case that did it, but there's like a comment and they didn't know what to do about it. We recommend that Tor adopt the Alt1 weights. Unfortunately, changing the consensus weights, these positional weights, would require a new consensus version. And it will require all the directory authorities to adopt it, so it's not an easy patch that they could just roll out and kind of incrementally to the clients. I would say that Tor has a plan going forward for how to use the weights. It's called Tor Proposal 265. Our goal-based approach is compatible with that, and we describe in the paper how that would work. And while this is the very Tor-centric paper, and we were starting from Tor, similar anonymity systems like Loki or Orchid or I2P would have similar issues. They make 3-hop circuits. They have limited relays that can start in the first position and the last position. And if they tried to load balance Tor, which they are doing in the way that Tor does well, generally, they would have similar issues. And so our solutions could be applicable to those systems. So that's what we found, and thanks for your attention.
Okay, thank you. Any questions? None, Zulip? Anyone in the room? No? Okay. Roger?
So exit traffic is like an actual fixed amount because either a Tor relay is an exit relay or not. Either it will let you exit or not. Whereas the guard side is more like an artificial decision made by whatever algorithm we want to do. So there's a lot more flexibility on giving more guard weight in the network or taking it away. Is there anything you can do with that to improve performance, with that observation that exits are fixed but guards are arbitrary and changeable?
Yeah, that's a good question. We consider only this, but there are other ways that you could redesign the network. So the two criteria for the guards, the uptime and the minimum speed. One of those is maybe a security or stability goal. I mean, how much do you want to get rid of the uptime or lower the uptime requirement if you're deficient to the guard bandwidth? That's not clear. Similar for minimum guard, the minimum guard bandwidth. If you lowered that, you would get more total bandwidth, but that might make the client's individual experiences worse. So it's not clear what the trade-off there would be, although you could make that trade-off instead of just taking that as given and then trying to balance across positions. Yeah.
Yep, it's a complex optimization problem.
Hi, I'm just curious whether it's possible to improve on this further by just having the directory servers report on how full everyone's capacity is, like how congested every node is, and that way any kind of imperfection in the load balancing algorithm the client uses can be corrected by just avoiding hotspots in the network. But I guess maybe that'll have bad anonymity implications, but.
Yeah, actively measuring the use of the Tor bandwidth in reality rather than expectation or in theory is not a thing that Tor really does very much right now, in part because if it tried to measure how much is being used at any given time in the network and made that publicly available, that would kind of reveal how the network's being used, which isn't great. Also, it would require a measurement infrastructure, active, accurate, in real-time measurement structure that they don't really have. There are client-side approaches to this sort of dynamic measurement-based relay selection approach, one where like clients will do measurements on their circuits to see which ones are faster and prefer circuits that appear to be faster. That's, I would say, sort of orthogonal to this. It might help you achieve what you were trying to achieve in expectation or in theory better, but it's also just a very different approach that we didn't consider.
Okay, I think that's all we have time for at the moment, so let's thank the speakers one more time.